coming Monday, you're going to write JEE Advanced Pattern exam, and syllabus for that exam is ionic equilibrium up to buffer solutions. So not thermodynamics. Don't worry. I repeat again, syllabus for coming exam, ionic equilibrium up to buffer solutions. Students, okay? Got it? Hello? Students, can you hear me? Okay, right. So students, in last class, successfully we completed second law of thermodynamics, and next third law of thermodynamics. What is third law of thermodynamics? Students, at 0 Kelvin or minus 273 Kelvin, it is called absolute zero temperature. At this temperature, any kind of gas definitely solidify. If it is solidify in a perfectly crystalline order, suppose if you take carbon dioxide or any kind of gas, if it is subjected to low temperature at 0 Kelvin, all carbon dioxide molecules perfectly ordered at this temperature, no atomic motion, no molecular motion, no disorder in arrangement. We can say simply no disorderness in the system, no randomness in the system with respect to molecular motion, atomic motion, disorderness in the arrangement of molecules. So at this particular temperature, entropy of the system is considered as zero. That is third law of thermodynamics. Very simple. At absolute zero temperature, the entropy of perfectly crystalline solid is zero. Students, that is third law of thermodynamics. So write down. At absolute zero temperature, the entropy of a perfectly crystalline solid is taken as zero. So why zero? At this temperature, no atomic and molecular motion in given system, and all are all molecules and all atoms are arranged, are they located in a particular location without any disturbance in the arrangement. So all are arranged in their location or in their places without any disturbance, without any without any change. So any disorderness we cannot expect from this crystalline solid. That's why at absolute zero temperature, the entropy of the system is considered as a zero. Suppose at absolute zero, they have given entropy of a system is not equal to zero. Then you can say it is not perfectly crystalline solid. There is some impurity in the crystalline solid, or there is some disorderness in the crystalline solid. There is no proper arrangement. There is still some disorderness. So if you in question, if you see at 0 Kelvin, the entropy of system is not equal to zero. Now you can say it is not perfectly crystalline solid. Students, do you understand? And what is the use of the law of thermodynamics? Yes, it is very important to find absolute entropy of the any system. And we already studied entropy is a state function. It is an extensive property. It is very difficult to find exact value of entropy of any system, because how can we find? We can find change in entropy. Always we can find change in entropy, change in Gibbs free energy, change in internal energy. But in case of entropy, we can find absolute entropy with help of this. Example, if you give carbon dioxide to me, I can convert this carbon dioxide from given state to 0 Kelvin state. I mean, if you give temperature to 27 degrees centigrade, if you give to me, I can convert this carbon dioxide by using temperature at 0 Kelvin. I can take the change in entropy from A to B. Already B is zero. So definitely the change in entropy must be equal to the state of A. Are you getting or not? Students, so please write down this. I will explain again. Third law of thermodynamics. Students completed. Okay. And what is the use of third law of thermodynamics? Abhinash, just I am giving some example. What is the use of applications of third law of thermodynamics? The first and most important application is we can find out absolute entropy of any system with help of third law of thermodynamics. Example, a system at take water or anything. Example, water. If you give water to me at room temperature 298 Kelvin, or yes, or in centigrade it is 25 degrees centigrade. Let's say this is water. I can convert this water into solid form exactly at 0 Kelvin. Okay, by applying temperature. Now change in entropy delta S for this is initial minus final. What is final? Entropy of H2O at 0 Kelvin minus 2O at 298 Kelvin. The change we can observe with help of delta Q by T. Those are the equations. Okay. And it is already 0 because entropy of any perfectly crystalline solid at 0 Kelvin 0. If it is 0, remaining delta S, what we observed is definitely equal to this system. Are you getting or not? Students, say yes or no.
Yes, sir.
No reply. Okay. So students, okay. Let us consider a system A at 0 Kelvin. It is at 0 Kelvin. If it is changes to another state at another temperature T Kelvin. State is different but same system. Now delta S for this equation is dq by T. We know the equation for delta S. Generally, chemical processes or some physical processes mostly at constant pressure. Let us consider it is at constant pressure. We are doing this at constant pressure. At constant pressure, the heat energy is called enthalpy. Okay. dH by dt equal to Cp, molar heat capacity at constant volume. If I write this dq as a dH at constant pressure, then dH I can write as Cp dt by T. And integrate this delta S from 0 Kelvin to T Kelvin, 0 Kelvin to T Kelvin. So better for it is S initial to S final. What is delta S? S1 entropy at 0 Kelvin minus entropy final. Final means initial delta S. Okay. So students, here it is entropy at T Kelvin, entropy at 0 Kelvin. Cp, it is we can write as ln T, ln 0 is 0. Okay. Entropy at 0 Kelvin for any crystalline solid is 0. If it is 0, directly you can find entropy at T Kelvin with help of this equation. And this equation for n number of moles, we can write 2.303 NCP log T. So student, this is the equation for finding entropy at T Kelvin. Are you getting or not? With help of the law of thermodynamics, I can calculate absolute value because already entropy of that crystalline solid at 0 Kelvin is 0. If it is 0, remaining is what? Entropy at T Kelvin. Understood? Say yes or no, Nana. Are you getting or not? Okay, right. Please note down this. Students completed. This system A at 0 Kelvin, B at same system at different states. Completed. Okay. So next students, standard entropy, standard Gibbs energy, delta S naught, delta G naught. If you see standard entropy, standard Gibbs energy, standard enthalpy, if you measure entropy of the system at 1 atmospheric pressure, 298 Kelvin, and that is called standard entropy, standard energy, Gibbs free energy. The change in entropy at 1 atmosphere, 298 Kelvin, is called standard entropy, standard Gibbs free energy. Okay, right. And finally, in thermodynamics, zeroth law of thermodynamics. Students, after establishing first law of thermodynamics, second law of thermodynamics, after that, zeroth law of thermodynamics was introduced. It is actually most fundamental principle. What is zeroth law of thermodynamics? There are three systems: A system, B system, and C system. A system, B system must be physically contacted each other. Even A system must be physically contacted with the C system. Even B system also physically contacted with the C system. So all are physically contacted. If A system, B system at same temperature is same, then there is no flow of heat, and that is called thermal equilibrium. Thermal equilibrium means if two systems are at same temperature, there is no flow of heat. That is called thermal equilibrium. If A system, B system are at thermal equilibrium, and A system, C system are at thermal equilibrium, automatically B system and C system also in thermal equilibrium. That is zeroth law of thermodynamics. Okay, so students here, if two systems separately in thermal equilibrium with third system, then automatically all are in thermal equilibrium. So it is zeroth law of thermodynamics. Thermal equilibrium means systems at same temperature. So no flow of heat. All are in thermal equilibrium with each other. Students, in thermodynamics, we studied four laws. Zeroth law is negligible, leave it. First law of thermodynamics, second law of thermodynamics, third law of thermodynamics. For exam point of view, for competitive exams, first law of thermodynamics and second law of thermodynamics, very, very important. So if you observe from first law of thermodynamics, we studied conversion of heat into different forms. Work done in isothermal process, in reversible process, in irreversible process, work done in adiabatic process, in reversible and irreversible process. So conversions, heat conversions, work done, internal energy, very, very important. And coming to second law of thermodynamics, nothing but entropy. So second law of thermodynamics given because to explain direction of the reaction, whether the reaction is spontaneous or not, and why it is not spontaneous. So we can explain with the Gibbs free energy delta G equal to delta H minus T delta S. Okay. Second law of thermodynamics explains spontaneity with entropy term. Entropy nothing but disorderness of the system. And coming to third law of thermodynamics, at absolute zero, it is also about entropy. At absolute zero, entropy of perfectly crystalline solid is taken as zero. Students, please practice questions from thermodynamics. If you do number of questions, definitely you can understand the theory part in a better way. So solving questions very important, because we don't expect any theoretical question in examination, particularly JEE mains and JEE advanced, only numerical based questions from thermodynamics. No theory questions. Students, understood? And definitely in chemistry, most of the questions are theoretical questions, because in organic chemistry, mostly from theory part. But physical chemistry, only numerical based questions. So who can solve questions from physical chemistry, definitely they will get good rank. Suppose questions from thermodynamics, some students only can solve that questions. So who can solve that question, they have good rank in examination. So that's why I try to do more number of questions from physical chemistry, particularly for chemistry. Okay, right. So students, this is about thermodynamics. And applications of thermodynamics we must study. That is second part of chapter. This is first part, students. Second part is thermochemistry. Students, previously in JEE mains pattern, actually 30 questions are given. Okay. In 30 questions, from thermodynamics, one question they have given. From thermochemistry, one question. So total two questions every year, actually they have given in a question paper. But now 25 questions only. In that, only one question from thermodynamics, maybe from thermochemistry, maybe from thermodynamics. But in I8 advanced, the weightage of this chapter is very high compared to remaining physical chapters. So second topic is subtopic in that, thermochemistry. So what is thermochemistry? It is nothing but applications of thermodynamics in chemical reactions. So with the help of thermochemistry, we can easily understand heat energy changes associated with chemical reactions. So students, write down here. It deals with heat energy changes associated with chemical reactions. This chapter deals with heat energy changes associated with the chemical reactions. For a chemical reaction, reactants converted into products. Students, reactants converted into products mostly at constant pressure We proceed the chemical reaction at constant pressure, sometimes at constant volume. At constant volume. At constant volume, at constant pressure, the change in heat energy, generally students, at constant pressure is called delta H, enthalpy. At constant volume, delta U. So students, here in chemical reactions, generally heat energy changes measured with help of two terms, only two terms. One is delta H, another one is delta U. Internal energy, enthalpy. And the relation between delta H and delta U is delta H equal to delta U plus P delta V. So we cannot use delta Q for chemical reactions. Reason, mostly at constant pressure, mostly at constant volume. So delta Q terms converted into delta H and delta U. The relation between delta H and delta U, we know already from first law of thermodynamics. Delta H equal to delta U plus P delta V. In a chemical reaction or in a chemical change, suppose solids converted into liquids, liquid converted into solids, solids converted into solids. Sometimes possible is the graphite converted into diamond. Okay. So generally, if solids and liquids are present, only solids and liquids are present, then there is no pressure effect. Correct? Because pressure effect is negligible on solids and liquids. There is no pressure effect. If there is no pressure effect, there is no change in volume. Volume is zero. Change in volume is zero. There is no expansion of solids. There is no compression of solids during chemical reaction. So how can you say volume change during that reaction? Definitely not. So in that case, delta H equal to delta U plus P delta V. P delta V definitely zero. Then equation delta H equal to delta U. So what is the exact meaning of delta H? Heat of reaction measured at constant pressure. What is delta U? Heat of reaction measured at constant volume. So for solids reactions, for liquid reactions, there is no differentiation between delta H and delta U. Both are same because there is no change in volume. Students, solids and liquids are incompressible. If you apply pressure on solids and liquids, they do not compress. Then how can you say pressure effect on solids and liquid reactions? So if there is no pressure, there is no change in volume. So delta V considered as a zero. Got it? Students completed. Students, chemical equilibrium we already studied. In that, we studied that there is no pressure effect on solid and liquids present in a equation. Only gases. Because solids and liquids do not compress, then there is no pressure effect. Okay. But in a chemical change, in product side or reactant side, suppose gases are present. Case 2, for gases, maybe reactant side you can see gases, maybe product side you can see gases. For gases reactions are not particularly gases reactions. For gases, P delta V we can write as a delta nRT according to ideal gas equation. P delta V equal to delta nRT, where delta N is number of moles of gaseous products minus of number of moles of gaseous reactants. Example, CaCO3 solid on decomposition, CaO solid plus CO2 carbon dioxide gas. Now, what is the relation between delta H and delta U? Delta H equal to delta U plus P delta V. P delta V we can write as delta nRT. Delta H equal to delta U plus delta nRT. Where delta N value, number of gaseous products 1, here reactants 0. So finally, delta H equal to delta U plus RT. So this is the relation between delta H and delta U. In case delta N equal to 0, then again delta H equal to delta U. Students, are you getting? Here delta N, change in number of moles of gases products minus number of moles of gases reactants. According to P delta V equal to PV equal to nRT, and it is from ideal gas equation, so that it converted into P delta V equal to delta nRT. So change in volume we can expect from change in number of moles. Here delta N is formula number of moles of gases products minus number of moles of gases reactants. Here products are how many moles of gases are there? Only one. CO is solid, CaCO3 is solid. So 1 minus 0, 1, delta N value 1. Then delta H, delta U relationship is delta H equal to delta U plus RT. Understood? Students completed? Okay. Calculate the difference between heat of reaction at constant pressure and constant volume for the combustion of acetylene at 27 degrees Celsius in kilocalories. Option A 0.9, option B minus 0.5, option C minus 0.9, option D 0.5.